Machine learning. In its most basic form, machine learning is using some computer or server to take data and train a model with it. This model can then be used to predict something similar to the input data that it was trained on. For example, consider an application on your phone that can label what you just took a picture of. But where would you get all those photos to train with? A simple idea is to get images from multiple sources. For example, a bunch of people could upload their photos of pets to a central server that creates a model from those images. But this is a big privacy concern, and privacy would be an even bigger issue if medical data was involved. This is where federated learning comes in. Instead of sending data directly to the server, each client device will train their own model locally first. Only these client-trained models are sent to the server. The server averages these models through a process called federated averaging to create a global model that can be sent back to each client to use and further train on. Let's consider another example. To proactively respond to natural disasters, machine learning can be used to improve predictions. In particular, consider a scenario where sensors are placed in areas of interest that are also in the middle of nowhere, meaning they are difficult to reach and communicate with. A federated learning setup would theoretically let each sensor create basic models to use locally as well as learn from other sensors far away. But hard-to-reach devices mean they must be resource-constrained to run for long periods of time. We define a resource-constrained device to be one that has some combination of limited time, compute resources, bandwidth, and power. The problem here is using severely constrained devices could take too much time to train and send a full model. Or certain resources can run out, such as memory or power, before a full local model can be generated. These problems can be addressed by using smaller models. Pruning is one technique that can be used to sparsify a model by removing non-essential connections. Basic pruning removes or prunes weights that are below a certain threshold. This results in a smaller network that will be faster to upload and compute on.
All this combined is our solution to collaborative learning under resource constraints, a project proposed by our faculty mentor, Dr. Harris Vikalo. Our problem is that it's difficult to perform intensive machine learning on resource-constrained devices due to limited compute resources and high communication costs. Our solution is to split up the model across multiple devices and decrease model complexity through federated learning and pruning. We want to use model pruning to minimize bandwidth while maintaining accuracy on resource-constrained devices in a federated learning environment. This gives us an inference speedup, a model transfer speedup, and less than 5% accuracy loss.
To perform federated learning, our team leveraged a Python library called Flower. For our central server, we used an Ubuntu machine, and for our resource-constrained client devices, we used 4 Raspberry Pi 4s.
To design and implement our model, the team leveraged 3 popular machine learning components. First, we utilized PyTorch, which is a Python library that facilitates deep learning training, inference, and model customization. PyTorch provides insightful tools for collecting metrics about the model, such as accuracy, training status, and inference times. Using PyTorch, we constructed the ResNet 18 model to analyze the training and optimization techniques of our system. ResNet 18's architecture consists of 5 convolutional layers, a pooling layer, and a fully connected layer to classify data. The data we chose to train and test our system on was the Fashion MNIST dataset. This set consists of 10 classes of familiar clothing items, such as t-shirts, shoes, coats, and dresses. Our training set consisted of 60,000 images, which were shuffled and appropriately distributed on the edge devices for unique model training in the federated learning process.
Finally, we created a GUI using PyQt5 that facilitates a data scientist's interaction with the training system and allows the user to run inference on an existing image or a newly taken image from the Raspberry Pi camera. In the Train tab of the GUI, the user can specify a bunch of inputs, such as server port, model, learning rate, degree of pruning, as well as which clients to use. When training is started, the server output is shown on the GUI. All server and client outputs are also saved in real time to the device you are running the GUI on. In the Inference tab, the user can connect to a specific client, then choose if they want to run inference on a newly taken picture using the Raspberry Pi camera, or use an existing picture on their device. Pictures used for inference are saved to the device they're running the GUI on, and all pictures are pre-processed into a 28 by 28 grayscale image before it is fed into the model for inferencing.
The team modified the Flower communication protocol to leverage model sparsity by transferring compressed models. Model upload and download times from each client were measured and charted. As expected, the longest upload and download times are derived from the baseline 0% pruned model, while the shortest times are from the 95% pruned model. Thus, upload and download speedup can be calculated to be 2.2 times and 7.5 times respectively. Additionally, since upload takes significantly longer than download, the estimate of the total time saved from pruning, around 35 seconds and 14 seconds respectively, highlights the benefits of addressing the uplink bottleneck in edge computing. These results support the claim that pruning can be an effective part of a solution to enable more efficient edge device machine learning.
To measure the speedup and inference times, the team ran time predictions of an X% sparse model through the deep sparse engine, where the times were charted against the baseline speed measured at the 0% sparsity. Deep sparse proved to be highly effective in illuminating the benefits of injecting sparsity into this deep learning network. Not only do the sparser models save more space on disk, but they also exponentially reduce the amount of time to perform their tasks. Within the maximum test accuracy loss of 5% from baseline, pruning to a sparsity of 95% produced a 5 times faster predictive model. The only caveat to this result is the hardware requirement of the dsparse engine. The engine requires certain CPUs, which are more powerful than ones that were found on the Raspberry Pis. So in the experiment, we ran the inferences on the laptop server. But given the state of processors and many modern edge devices like the iPhone, this hiccup does not prevent the conclusion that inference speedups will be transferable to such edge devices.
In conclusion, on a 90% pruned model, we successfully maintained greater than 90% accuracy, decreased the size of the model by over a factor of 5, and sped up inference and upload times over 200%. This means all our objectives are met and, most importantly, prove that federated learning with pruning is an effective first step to achieving efficient machine learning on resource-constrained devices.
These are some possible extensions that can build off of the results of our project. First, adapting the backpropagation algorithm to leverage sparsity in the model so that the training phase can also experience a speedup similar to the inference phase that was experimented on this project. Secondly, introducing weight regrowing to the edge devices such that edge device models can grow back some of the weights that have been zeroed out by the central server to take advantage of the local non-IID data that they may have. And lastly, quantization, which would further speed up the inference and the training phase by simplifying tensor operations.
Thank you for watching, and we hope you enjoyed learning about our project.